Morning, everyone. How are we doing? Questions before we begin? Aquafina. I know it's just distilled water, but it's really just for the bottle. Geometric series is the only thing we can take for granted. Yeah. Hayden is asking if we're going to have review today. Well, I mean, if you have questions, we can do some. Otherwise, we're going to go right ahead and do new material. No complex numbers on the midterm. Not even sine and cosine. When in doubt, don't take anything for granted. Take 30 seconds and write out derive the sine series if you need it. Can we do a problem where we have to prove something? Tiffany, did you have an example in mind? Nick is asking what happens if the error changes the decimals of the approximation. What do we do if it does? You go further down the line. You have to make sure that they don't change. We started with an error which was less than the halfway to the other decimal place, if you will. That wasn't enough in the case that you're suggesting. Binomial series is material that could be on the midterm. Dan has an example. Can we do 56 in the review section? I don't know what the review section is, but if it's what you do in the workshops, then, that's really material for the workshop. Oh, maybe, Alessandra, maybe you meant in the back of the book. I don't have the book with me, so if you've got questions, go ahead. Dan is approximate the definite integral to within the indicated accuracy. And what is the accuracy there? So 5 times 10 to the minus 6. Very well. Very well. So I was was going to say binomial, but you understand the issue with the binomial theorem, right? If you use the binomial theorem, if you treat this as 1 plus x to the 4 to the 1/2, which is seemingly the thing to do. So you know that this is 0 to infinity, 1/2 choose n, x to the n, so x to the 4 to the n, right? The problem is, oh, well, I was going to say there was a problem, but there isn't, right? There isn't a problem because, so it's a good thing we wrote it down, right? I mean, what is that? This is 1/2 x to the 4n. I mean, x to 1/2. We'll get there. It's 1/2, right? I mean, it's not even 1/2. It's 1. Jesus. And then I'm not a big fan of that notation, so why don't we work it out? This is 1/2 minus 1/2 minus 1, 1/2 minus 2, all the way to 1/2 minus n plus 1 over n factorial, right? So and this is from 1 onwards. So it's this plus, when n is 1, it's 1/2. Yeah, so just 1/2 x to the 4, and then when n is 2, it's 1/2 minus 1 over 2 factorial, x to the 8, and 1/2 minus 1, 1/2 minus 2 over 3 factorial, x to the 12, and so on and so on. It doesn't look like it, but the important thing to recognize is that this is actually an alternating series, right? This one is positive. Here, 1/2 minus 1 is going to be negative, which makes this whole thing negative. And then this is negative, but that's negative, so the whole thing is positive, and so on and so on. There it is. So this is actually alternating, which helps us quite a lot. So if we're integrating this, what do we get? Well, I mean, first of all, let me point out, maybe you're thinking to yourself, this is positive and that's positive, so it's not alternating, correct? But the first term, I mean, the first few terms don't matter. As long as it's ultimately alternating, that's really all that matters. And somebody's asking, can't we use integral approximation? Well, I mean, you can do whatever you want. I think this is going to be easier-ish, maybe. So if we integrate this, what do we get? X plus 1 over 2 times 5, x to the 5. Times 9, x to the 9. Right, I mean, the question isn't forcing you to do one specific way. So as long as, you justify everything, it's going to be fine. Let me throw in one more. I suspect that's going to be enough. 1/2 minus 1, 1/2 minus 2, 1/2 minus 3. Over 4 factorial. This would have been x to the 16, so 17 x to the 17 between 0 and 0.4. So really, what we're seeing is that this is equal to 0.4 plus 1 over 10, 0.4 to the 5. Plus 1/2 minus 1 over 18, 0.4 to the 9. This is 6, so 78. 0.4 to the 13, and this term here can somebody work out using Wolfram alpha or whatever what this last term is? This one right here. I suspect, or I hope, that it's going to be enough. Would a problem occur when the series doesn't alternate? Exactly, right, Alessandra? That's the issue. If the series doesn't alternate, we're in trouble. So something else has got to be done. So you would have to use Lagrange, and that's what I thought was going to happen originally. That's what I thought was going to happen originally, but luckily we wrote it down and we noticed that it was alternating. All right. This is 4e to the minus 10 or minus 6 something to the minus 10. So a lot less than that, right? So I think it's enough. What about the next, what about the previous one? So this is apparently minus 6.5, 10 to the minus 10. What about this one here? Gabriel, minus 3 to the, so I mean either way, whether it's minus 6 or minus 3, still small enough. What about the previous term? Malloy for the previous term? 6 times 10 to the minus 9. So still small enough. What about the previous one then? Plus, right, the 0.4 to the 13 alone does it. I'll believe it. What about this one? That one might do it as well. But it's not alternating before the third term. Well, I mean, these two already alternate. And then it keeps alternating after, so we're good. Minus 3.4, 10 to the minus 6, which is good enough, right? Minus 3.4, 10 to the minus 6. But I suspect this one will not do it though, because right, we're almost there. So, conclusion. So in other words, this is equal to 0.4 plus 1 over 10, 0.4 to the 5, and that error is to within this. Yeah. Excellent. There it is. And this is to within. If you want to be complete there, this is to within 3.4, 10 to the minus 6. Very nice. I mean, that is what we're using, Dan. We're using the conclusion with the alternating series test. Somebody's asking why it's a problem if it's not alternating. Because you can't use the alternating series test, exactly. All right. Questions? I think Alessandra had a question originally. Of course, we want it to be less than 5 times 10 to the minus 6. We did use the alternating series test business. I mean, we did not justify that the terms were decreasing. It's a bit difficult to do so here. Is it? No, it's not. It's not. Well, it is. It is a bit difficult to do so here, so we just made that assumption. Taylor's inequality. What does Taylor's inequality say? Taylor's inequality says if you have a function which you can differentiate n plus 1 times, this is Taylor polynomial of degree n plus the remainder of degree n. And so, I mean, of course, you understand, first of all, what is this? Well, let me change it to big N. Where this is your Taylor polynomial of degree n, and this is the rest. But we have a nice theorem known as the Lagrange remainder theorem, which tells you that this is actually equal to this for some value of z, where z is between x and c. Follows from the mean value theorem. We didn't prove it, but you can assume it. So the point is, if you bring this to the other side, you see that f minus t is your remainder. So the remainder is actually, Matthew's asking why isn't it r to the n plus 1? It's just notation. They use the same method. How do you find z? Well, exactly. You don't. The fact that z exists follows from the mean value theorem, but you never need to find it. You just need an upper bound, exactly. If you can bound this, then you've bounded the error. But how do you get the upper bound? Well, there's no formula to get the upper bound. You need to think. You need to know how the nth plus 1 derivative behaves. And this is very dependent on the function. Exactly. If you know that the nth plus 1 derivative is less than or equal to n, you're good to go, right? The difference between the function and your Taylor polynomial is the remainder. So this is your error. It's how large the difference between your approximation and the actual function is. That's all. So this is your error, and it's this. So if you can bound that, you're good to go. Is that enough info to try to find m? As it is, here there's absolutely no information. So you're not going to be able to find m. But if you're given an actual function, then yes. If you're given the function, you can find what m is. I want to say that this is usually enough, but who knows? You should be familiar with Taylor's inequality as well. Well, what are you trying to do? You're trying to find the maximum of this expression. You know how to maximize a function. We spent all of Cal 1 trying to do that. No, that is, James, that is not the error. That is the approximation. That is like your Tn, right? It's we in fact use the Taylor polynomial of degree 5 to approximate. That's your Tn. And the error was the rest. Exactly as the alloy suggests, some of the functions are simple. If you take sine or cos, you know the derivatives are always less than or equal to 1. Exactly that. but some of them are not so simple. Exactly. But you're restricting your attention to an interval. You know z is between x and c. Gabriella, we applied not the alternating series test per se, but the result that you can add as many terms as you want and the error is less than the next term in line. So that's why we only had to make the next term in line less than this. So Chloe M, which is the largest, which is an upper bound for this, would be 1, exactly that. Yeah. All right, let's move on back where we were last time. We were looking at partial differentiation. We were extending the notions of partial differentiation to higher, extending the notion of differentiation to higher dimensions. And Eloy's asking, not sure for ln x, if your nth derivative is ln x, you know the graph of ln x. And if you're restricting your attention to some interval, maybe both x and c are bigger than 0. So you know ln is an increasing function, so the maximum is going to occur at, you might be able to use that, but you don't even need to. Ln is an increasing function, maximum occurs at the rightmost endpoint. Of course, if one of them is positive and the other one is negative, you want to bound the absolute value, so you're going to have to do a little bit of work there, but very little. We were looking at partial differentiation, and one important notion in differentiation was the idea of implicit differentiation, when you don't have y explicitly written as a function of x, but rather an equation involving x's and y's, where you might not be able to actually isolate for y. You can still find dy dx. Here, imagine the scenario where you have an equation involving x, y, and z, where you might not be able to isolate z as a function of x and y, but where the equation implicitly defines z as a function of x and y. Case in point, consider this. Here we don't have z equals a function of x and y, but rather an equation which implicitly defines z as a function of x and y. Can we find dz dx and dz dy? Assuming z is a function of x and y. Well, in the same way that we did in the one variable case, where we would just assume y is a function of x and differentiate both sides. The same is true here. The same is true. Assume z is a function of x and y and differentiate both sides. So we have this. Differentiate both sides with respect to x, assuming x and y are independent variables and z is a function of x and y. Exactly the same process we did in the one variable case. Derivative of x squared is 2x. Derivative with respect to x of y squared is 0. X and y are independent of each other. When you differentiate with respect to x, you treat y as a constant. Derivative of z squared, well, it's something squared, so 2z times the derivative of the inside. Z is understood to be a function of x and y. So derivative of the inside, dz dx. Derivative of 4 is 0. Factor out a dz dx. I mean, leave the dz dx on one side, everything else to the other. Factor out and divide. You know where this is headed. Z is equal to x over 1 minus z. Here you get a function of x, y, and z in the same way that in implicit differentiation in Cal 1, dy dx would have been a function of y and z. It's the best we can hope for, but it does the trick. Repeat. Differentiating the whole equation with respect to y. Differentiate the whole equation with respect to y. Derivative of x squared is 0. Derivative of y squared is 2y. Derivative of z squared, again, 2z times the derivative of the inside. Chain rule, right? dz dy. Minus 2 dz dy is equal to 0. Same as before. It's easy to see that dz dy is y over z minus 1. How are we doing here? Do we want to see another one? Why is there no dx dy, David? It's a valid question. Somebody want to address that? Z is a function of x and y, that's right. But x is not a function of y, so dx dy is dx dy, x is treated as a constant when you differentiate with respect to y, that's right. They are independent of each other. Right, a separable equation for those of you taking 2, 6, 3. Very nice observation there. And those taking 2, 6, 3 had to learn partial differentiation on their own, because we hadn't gotten there yet. But I mean, I'm sure you picked it up instantaneously, because there's really not much happening there. Same question, we're looking for dz dx and dz dy. Right, you only did ODs, not PDs, but still, when you were doing exact equations, you essentially did partial differentiation. However, I mean, you're getting a nice feel for ODs. Let me warn you that PDs, completely different. Completely different. Much harder and more demanding. So consider this. And again, differentiate the whole equation with respect to x, assuming z is a function of x and x and y are independent variables. David, this is what we've been doing when we were differentiating. We did the partial derivative last time, and I showed you that when you differentiate with respect to x, you're really treating y as a constant. This follows from the definition. So differentiate the whole equation with respect to x, treating z as a function of x and y, but x and y as independent variables. So the derivative here, y is a constant, derivative of z is dz dx. Derivative of x is 1, ln y is a constant, and 2z dz dx. Bring this to the other side, factor out and divide. Can we do that in our heads? And if you repeat, taking the derivative with respect to y, here y and z are functions of y, so product rule applies. Differentiate the first one, leaving the second one fixed. Plus leave the first one fixed, differentiate the second one. This is constant. And the derivative of z squared, 2z dz dy. Again, bring the dz dy's to one side, everything else to the other. Factor out and divide. We see that dz dy is z plus x over y all over 2z minus y. Again, very simple and straightforward. Nothing much is happening here. It's an immediate extension of implicit differentiation in the one variable case. What I might point out is that the denominators are the same. And if you look at the previous question, you have the same denominators there as well. Is that just coincidence? It is not. Why is the first term z and not dz dy? Somebody want to address that? We're going to see another way to view this, a generalization, if you will, that will tell us why the denominators are always the same. Right here, you've got a product, y times z, so product rule applies. Thank you. Yeah. So in maybe next week, we're going to see another way to do this implicit differentiation, a way that extends to how many dimensions you may have. And it actually tells us that you can solve for z as a function of x and y, assuming this denominator is not zero. Nilloy, probably not. I don't see, well, I don't know. I'm going to let you try that. I'm going to let you try that, see what happens. I don't know if anything interesting comes out of that. Yeah, I don't know. Last time we were doing first and second order, well, or higher order partial derivatives, right? Let's go back to this example and find all these second order derivatives. dz dx. Well, this is arctan of something, so you know what the derivative of arctan is. This square plus 1 times the derivative of the inside with respect to x. It's a quotient, so quotient rule applies. Vu primed minus u v primed all over v squared. Maybe we want to simplify that a bit. The minus xy, this is minus xy, and this is going to become plus xy, so these will cancel out. And we get 1 plus y squared. And if I multiply this in, canceling out with this one, x plus y squared plus 1 minus xy. Can I expand that? Why don't we expand? Seems like the thing to do. This is x squared, 2xy plus y squared plus 1 minus 2xy plus x squared y squared. These cancel out. So we're left with 1 plus y squared over x squared plus y squared plus 1 plus x squared y squared. So that's dz dx. Let's look at dz dy. Which is going to be 1 over this. Squared plus 1 times the derivative of the inside. Again, quotient, so quotient rule applies. V u prime minus u v prime. And when I say v prime, I mean the derivative with respect to y. So that is minus x over v squared. And again, blah, blah, blah there. 1 plus x squared over the same denominator. All right. So, but that's only the first derivatives, the first partial derivatives. If we differentiate this with respect to x again, d by dx of dz dx, right? So the derivative with respect to x of this, well, luckily for us, the numerator is constant. So this is just going to be 1 plus y squared, that's a constant. And I'm going to treat this as this business to the negative 1. So when I differentiate with respect to x, this is just negative 1, that thing, to the negative 2 times the derivative of the inside with respect to x. So 2x plus 2xy squared. Naloy, I don't know that there is. I don't know that there's anything you can do here. But I know we're going to be smart and look at dz dy, which was this. And we're going to compare with dz dx. And I think you see the comparison here. If you change the x's to y's and the y's to x's, this goes from here to there. So when you do the second derivative, dz dx, d squared z by dx squared versus d squared z by dy squared, the derivative is going to be the same, but with x's and y's interchanged. So it's the same derivative, but with x's and y's interchanged. X's and y's interchange. That's very nice. I've cut our work down by a lot. Well, maybe not a lot. And what about d squared z by dy dx? So the derivative of this with respect to y. If we differentiate this with respect to y, what do we have? Well, we have quotient, so quotient rule applies. Vu primed so Vu primed minus u v primed minus u v primed 2y plus 2x squared y all over v squared let's leave it as that. Let's not simplify that. I hope we don't need to simplify. And if we look at d squared z by dx dy, which is the derivative with respect to x of 1 plus x squared, well, again, if we're smart, we recognize that it's going to be the same derivative, but with x's and y's interchanged. But let's not, as Gabriella suggested, should give us the same, and that's where I was headed with that. When I said I hope we don't need to simplify, because I was hoping that we were going to see that it was the same. I may have been optimistic here, because it might not be immediately clear. Let's do the quotient rule, Vu prime minus u, and that is not u, minus u v primed, which is 2x plus 2xy squared all over this squared. So first of all, observe that it's the same thing, but with the x's and y's interchanged, right? If you interchange x and y here, you still get the same expression. Interchange x and y, interchange x and y, and interchange x and y. Is it clear that this is the same? Well, first of all, the denominators are the same, so we can focus on the numerators. I did not want to expand that. Did not want to expand that. Did not want to expand that at all. I'm afraid we don't have any choice though. Let's just leave the denominator as is. If we expand 2x squared y plus 2y cubed, 2y, 2x squared y cubed, minus 2y minus 2x squared y minus 2y cubed minus 2x squared y cubed. Let's hopefully cancel some stuff. The 2x squared y cancel out. The 2y cubed cancel out. This and that cancels out. Oh, lovely. Everything cancels out. We're left with 0. That's unexpected. Is that expected? Have I made a mistake? 1, 2, 3, 4. 1, 2, 3, 4. We probably should have seen that somehow. Should we have seen that? Yeah, now we see it. Now we see it. We should have combined these two things together. This would have been x squared times 1 plus y squared, combined with this 1 plus y squared. You would have gotten x squared plus 1 times y squared plus 1, and the x squares would have canceled. No x's. There you go. Yeah. So, I mean, that should have been clear. And of course, this will give you 0 as well by the same reasoning. All right, well, I mean, at least we didn't make any mistakes. So, right, I mean, that illustrates the importance of simplification. So in this case, the second order mixed partial derivatives are 0, both of them. I mean, it's not always the case, right? But the important thing is that they were equal here. And I was hoping that this example would convince us that in many cases they are equal. Here it was perhaps a bit trivial, since the partial derivatives themselves were equal to 0. But this, I mean, if you look at the examples we were doing last time, we encountered questions where the mixed partial derivatives were not 0, but they were equal. So this brings up the obvious question: are they always equal, or under what conditions are the mixed partial derivatives equal? And as James is suggesting, this theorem is known as Clairaut's theorem. Let f be defined. Let f be defined. No. I'll give you f of xy. Let f of xy be defined on a disk containing the point AB, containing of xy and f of yx are both continuous. On the disk, then the mixed partial derivatives at the point are equal. Right, so Clairaut's theorem gives you a sufficient condition for the mixed partials to be equal. Let me point out that this is going to extend. Why is it a disk and not a plane? It doesn't have to be a plane. Really, it's a neighborhood. It's a neighborhood around the point AB. So if it's true for all values of x sufficiently close to AB, and that's why you have a disk. But it really doesn't matter. It could be an open set around AB, and that would be sufficient. This generalizes to fxxy equal to fxyx, right? Because if you apply this theorem to fx, then you get the other mixed partials equal. But this is also equal to f of yxx, and so on and so on. So in other words, if you have continuity of all the mixed partials, then all the mixed partials with the same number of derivatives of x and the same number of derivatives of y, they all have to be equal. Right? F of x, x, y, x, x has to be equal to f of x, 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 y, and so on, if everything is continuous in a disk around some point. It's exactly equal. The order in which you do the partial derivatives doesn't matter if everything is continuous in a disk. What do we mean by in a disk? We mean at all points in a disk, right? So you need the mixed partial derivatives to be continuous at all points in the disk. Suppose we wanted to find f of yxy. You know what this means. This means you differentiate with respect to y first, and then x, and then y. Why didn't we do interior point and boundary points? Well, that's essentially interior points of what? Matthew, this is correct as long as everything is continuous in a disk, right? We need continuity. No. It's not equal to f of x, y, y, right? It's not equal to f of x, y, y. Here you have two y's and one x versus two x's and a y. So if you have the same number of x's and y's, and assuming everything is continuous, then you're fine. So here, if everything is continuous, this is going to be equal to f of y, y, x, or f of x, y, y. Right, and you know how to find the derivative. Let's find the derivative with respect to y first. And you know that that is going to be 5 cosine 2x plus 5y. And if you differentiate that with respect to x, you know it's going to be minus 10. And if you differentiate that with respect to y again, minus 50 cosine of 2x plus 5y. Absolutely, thank you. Good shot. I will let you convince yourselves. Right here, we only found one of them. But if you, right, I mean, we found this one. If you find that one, and if you work out what this one is, you'll see that they're all the same. When aren't they the same? An excellent question. We'll take an example. We'll take the simplest example, which is already very difficult. Certainly, as Marine suggests, they cannot be continuous on a disk. Let's do this question first, though. Let us verify Clairaut's theorem. What does that even mean? You know what that means. Why is that still working? Jesus Christ. All right. Verify Clairaut's theorem. So Clairaut's theorem gives us equality of the mixed partials under the fact that everything is continuous. Let's work out du dx. That is easily seen to be y e to the xy sine y. And if you differentiate that with respect to y, well, now you've got three things multiplied together. You know how to do that, right? Differentiate the first one, leaving the other two fixed. Plus, leave the first one fixed. Differentiate the second one with respect to y. So x e to the xy, leaving the third one fixed. Plus leave the first two fixed, differentiate the third one, goes y. If, however, we differentiate it with respect to y first as a product, so product rule applies. X e to the xy, leaving sine y fixed, plus e to the xy cos y. And if you differentiate that with respect to x, product here, so product rule applies. E to the xy plus xy e to the xy, all the time leaving the sine y fixed. And finally, y e to the xy. Is this the same? Well, these two certainly are. And if you expanded that, you would get this one, this term right here, which is that one, and the other one there. Corresponding to that. Beautiful. How are you doing? Is there a formula for the nth derivative? You mean the nth partial derivative? Okay, I know. In general, I think it's going to be difficult to. Well, I mean, here we already have equality of the mixed partials, right? So that's the conclusion of Clairaut's theorem anyways. We don't actually have to argue continuity, but you could, right? You know the exponential function is continuous. You know polynomials are continuous. So the composition is continuous as well, and so on and so on. Well, right. We only prove the second order. I mean, of course, we're going to stop here. But as we suggested, Clairaut's extends to higher orders. But yeah, I'm quite certain they only meant second order here. We did not assume the two mixed partials were equal, right? We worked them out separately, and they turned out to be equal. And then if you look back, of course, every piece is continuous. So, of course, they were equal by Clairaut's theorem in the first place. Let's consider an example where they are not. Yeah, that's interesting. Proving Clairaut's theorem using the definition, the limit definition, probably works. You'd be working with two limits, possibly. It's not, and then you interchange the limits. I think it's doable. But let's consider this. I claim, so let's write down the claim, that the partial derivative with respect to x and then y is not the same as y and x. Yeah, exactly. As one suggests, it's not that hard, but it's pretty long. What I wanted to point out is that this is not an obvious function to take, right? If I asked you for an example off the top of your head where the mixed partial derivatives were not equal, this might not arise naturally. Let's for xy not equal to 0, 0, let's take the derivative. Well, I mean, Niloy brings up a valid question. Can we even differentiate? Certainly, if you're away from the origin, right? If the denominator is not 0, you're fine. You can differentiate. So let's differentiate. If you're not at the origin, what is the derivative? So let's differentiate this away from 0. And it's a quotient, so quotient rule applies. The u prime, the derivative with respect to x, 3x squared y minus y cubed minus u v primed all over v squared and what do we get? Let's expand that. This is 3x to the 4y minus x squared y cubed plus 3x squared y cubed minus y to the 5. The whole thing times 2x. Does anything cancel here? X to the 4y. Just one of these. So that is x to the 4y plus 2x squared y cubed. Actually plus 4, right? With this one at the end. Minus y to the 5, is that correct? X to the 4, this and that cancels. Give you that. X squared y cubed. So this, that, and that. All right, there it is. Does everybody have that? Matthew is asking, can we use what we learned a few classes ago about showing discontinuity using different approaches, like x equals 0, y equals 0, x equals y? Here's the thing. No, I mean, wait, are we back? Has it stopped buffering? There was never a buffer. Is that what you're saying? All right. The thing is, you know, you're thinking back to Cal 1, we have this nice theorem that says if a function is differentiable, it had to be continuous to begin with. And now you're thinking we're going to apply that here. But here's the thing. We don't have that theorem in this case. The partial derivatives may exist even if your function is not continuous. Because remember the way the partial derivatives work, right? It's just the derivative on one cross section, the derivative in the direction of x, or the derivative in the direction of y. That's all you need for the partial derivatives to exist. So in fact, your function doesn't even have to be continuous in order for the partial derivatives to exist. So we're not even going to bother asking the question, is this continuous? It doesn't matter. We worked out the partial derivative everywhere except at 0. Let me point out that, we're going to be smart. Instead of taking the derivative with respect to y of this, observe that if you interchange the x's and the y's, y cubed x and y x cubed, you get the negative of the function. So the derivative with respect to y of this is going to be the derivative with respect to x, but with a negative, and the x's and the y's interchanged. So it's going to be y to the 4x plus 4y squared x cubed minus x to the 5. I understand that it's difficult to see. So I'm going to let you work it out. Take the derivative of this with respect to y. It's just a quotient rule. You can do it inside of a minute or two. And convince yourselves that this is actually what you get. But now, the question arises, what about the derivative at 0? What about the partial derivatives at 0? What is fx of 0, 0? Right here we have the derivative everywhere except at the origin. What about the partial derivative at the origin? Well, let's work that out. You know what that is. That's the limit of h goes to 0 of f of 0 plus h, 0 minus f of 0, 0 over h. You have no choice but to do the limit definition. So what is this? When y is 0, where you see a y, it becomes 0, you have 0 over x squared, or 0 over h squared, which is 0. F of 0, 0, 0 over h, that whole thing is 0. And similarly, the partial derivative with respect to y at the origin, this is f of 0, 0 plus k minus f of 0, 0 over k. If x is 0, that's 0, that's 0, that's 0, so you're left with 0 over y squared. The whole thing is 0. So that is 0. Similarly, there is a course on Thursday. I mean, we have no more holidays. So, but on Thursday, I'm not, since the exam opens up when? Tomorrow, is it? I won't be answering any questions from tomorrow onwards. So no questions about previous material. You can ask questions about the midterm if there is like a mistake or anything. We might not be able to answer, but yeah. So let's put everything together. What have we seen? We have seen that the derivative of f with respect to x is this. if xy is not the origin, and it's 0 at the origin. And similarly, the derivative of f with respect to y is equal to this if xy is not the origin, and 0 if it's the origin. Yeah, it'll open up on CrowdMark. You will get an email at the time that it opens up. If you don't, please email me. Let's finish this up quickly. What is the derivative of f? Well, the derivative with respect to y of fx at the origin. By definition, this is the limit as k goes to 0 of fx of 0, 0 plus k minus fx of 0, 0 over k. Right, again, it's just the limit definition. You have no choice because it's a piecewise defined function. If x is 0 and y, well, first of all, fx of 0, 0, you know that to be 0. What is this? This is fx of 0k. Everywhere you see an x, you replace with 0. Everywhere you see a y, you replace with k. So this becomes minus k to the 5 over k to the 4. Does everybody see that? And of course, you recognize that this is really k, negative k to the 5 over k to the 5. So the limit is negative 1. And if you repeat with f of yx, which is the limit as h goes to 0 of fy of 0 plus h 0 minus fy of 0, 0 over h, I forgot the minus. Thank you. Right here, there's a minus. Thank you. That was going to be painful. So everywhere there's a y, replace with 0. Everywhere there's an x, replace with h. So that's 0, that's 0. So that is minus, minus. So that is a plus h to the 5. The y is 0, x is h, so that is h to the 4 minus 0 over h, which is easily seen to be positive 1. Exactly that. So you see that f of xy at the origin is minus 1, f of yx is positive 1. No. To find fx at the origin, you cannot differentiate the number 0 we had. That's just a function at one point. That tells you absolutely nothing. Right, in the same way that if you look at the function y equals x squared, when x is 3, y is 9, can you just differentiate 9? And the derivative of 9 is 0, but that's not the slope of the tangent line at all. That has nothing to do. So that's because it's not continuous at the origin. Well, I mean, we didn't even check if it was continuous at the origin. Who knows? But again, the point is that the functions don't need to be continuous in order for the derivative to exist. Here, though, what we can conclude is that for sure, f of xy and f of yx will not be continuous. So, I mean, this question, of course, does not contradict Clairaut's theorem. Clairaut's theorem told us that if these were continuous in a disk around the origin, then the mixed partials would have to be equal. So one thing we can conclude is that these are not continuous in a disk around the origin. So there it is. Thank you all for coming. Good luck on your midterm. And I will see you on Thursday. Well, I don't know that you can pick any function that isn't continuous. Right? All Clairaut's theorem is saying is that if the mixed partial derivatives were continuous, then they would have to be equal. It's not really proof-based, no. I assume you're talking about the midterm there, Mies, but yeah. All right, see you guys